This is going to be a tutorial video for the sum output algorithm for Python, which is a Python script that bins scans together while tracking species in mass spec files. In particular, it can get rid of a lot of noise, like you can see on this experiment right here. I've tested this script on output files from a Waters Qtopf Micro as well as a Waters Ultima instrument. In theory, it should work on any mass spec file, but those are the two that I've tested. The first thing that you're going to need to do is get a distribution of Python, so you can use whichever one you want. I happen to be using Enthought, which is what I'd recommend for anyone who's picking this up and has access to it. It is free for academics. You can get 1-year licenses at a time, so you'll have to request a license through that and install it. The other tool that you're going to need is ProDo Wizard, which is a tool that converts the proprietary mass spec files into something that I can parse using Python. So you're going to need to download that. You're going to need to choose whichever end user distribution is most appropriate to you, and download and install that with leaving all of the settings as default. The next thing you're going to need to do to get going is when you open up Canopy, you're going to want to sign in up here, and what that will do is it will give you access to the package manager, and you're going to need that because there are some packages that do not come with the native distribution of Enthought. So you're going to need to go into Package Manager after you've signed in. It's going to connect to the servers, and there's two packages that you need to install. The first one is OpenPyXL. If you select that and hit install, it's going to install it for you. The other distribution that you're going to need is LXML. There's going to be a few that are going to come up with that search, but you want specifically the LXML file one, and it's already installed on this distribution. So now that I've got those sorted out, I'm going to go to my Python script and I'm going to open it up in the editor, and that's it right here. And we'll just leave that for a second while we set up the Excel file that you're going to need. You're going to need a few things in order to get this going. The first is you're obviously going to need the raw file that you generated using your mass spec, and then you're also going to need an Excel file. And what we're going to do with this is we're going to set up the parameters for the Python script to process. So what you need to do is rename one of your Excel sheets as parameters. You can get rid of the other two sheets that it default opens. And then what we're going to do with this is we're going to tell Python where the peaks are and what to call them. So in the first row, there's going to be 3 columns. There's going to be name, start m upon z, and m, end m upon z. It doesn't matter what you put in these in the first row, it's going to be ignored by Python, so don't put a peak there, for instance. And what we need to do is we need to give it the information that it wants, which is the start and end point. So I have 2 main species in this mass spectrum. Zooming in, this is my substrate. So I've just summed that, and then this is my product. And so if I'm going in and I'm putting substrate as my name, if I zoom in over here, I can guess roughly where it is. I'm going to go with 478.8-ish, and then the end of that isotope pattern happens at about here. I'm going to go 41.3, just roughly guessing there. Instead of guessing, if you want to do it more precisely, you can go over into your chromatogram window, and those values are pretty close to what I just put in. So I can instead input 478.7, 41.3. And then the other one I want to trace or track is my product. So if we go back over here, we can guess that it's about 459. We'll just go with that. And then 461.4. Again, I could use these values or I can just guess. It depends on how much interference you're going to have around your peaks, the peaks of interest. So this is going to be up to you to figure out. One of the nice things about this script is that as long as you have a good calibration on every spectrum that you run, or every experiment that you can use these values to sum multiple experiments. You can just use these parameters over again. So now that I've got my two parameters set up, my two species, I'm going to save this, and I'm going to save this in the working directory that I'm working with. And this needs to be in the same location, as in the same directory as your raw file. As in, don't put it inside the raw file, it needs to be in the same directory. So I'm just going to call this Python example and autosave as a XLSX, which is what the Python script uses. Now that we've got our peaks defined, the next thing to do is to close the Excel file. Otherwise, the script will not be able to save to the Excel file if it's open. And then we go over to our editor, and there's a few things that we need to give this script in order for it to function. The first thing that we need to do is navigate to the working directory, and you do that using this arrow and change working directory. And we're going to navigate to the location of the raw file. So in this case, I've got it in this folder. So you want to navigate to the folder where the raw file is, not the raw file itself. Windows treats the raw files as a directory, but you should view them as a file. So root folder, select, so I've changed this to the working directory. That's the same directory of where I've put this Excel file, and I have the raw file. So we need to give it the raw file name, and I'm going to slow double click to select, Control C or right click copy, and then I'm going to insert it between these two quotation marks. It's important that it goes between the quotation marks for the script to function properly. So Control V pastes it, and then I'm also going to tell it the Excel file name, which is this one right here. Copy, paste, and then for this example I'm going to use number of scans to sum as 2. So the number of scans to sum is going to be however many number of these scans we want to put together and appear as a single scan. So we're keeping all of the same information that was present before in 2 scans, and then we're combining that into a single intensity value with the same time point. That's how this particular script is functioning. So in this case I'm going to do n equals 2. Now the script is all ready to go, and I just need to run it. So there's 2 ways of doing that. The first is this green play button up here, which is run the current file, or you can hit Control R, which is going to accomplish the same thing. So hit run, it's going to generate another file, and that's going to process through everything. And wait for it to finish. It gives you progress bar down in here, and it's done. So this thing that pops up is just a quick visual idea of what you've managed to generate, or what that n equals 2 has done. It shows you what the raw data looked like, what the n equals 2 sum did, and then what it looks like if you normalize it to the tick. And all of this data right here has been saved in this Excel file that we were just editing. Remember how there was only one sheet, that parameter sheet? It's now added a raw data, and so there's all of the intensity values for those peaks for all of the time points. And then there's 2 sum, which is the 2 scans summed together, and then that's those values in the normalized, that's normalized to the total ion count. And it also outputs a function chromatograms tab. This tab is more for Ultima examples, for instance. So you have a triple quad that's scanning a single ion. Those chromatograms will appear in this tab. In this case, all that we had to worry about was a tick, and that's the only chromatogram that's present here. So that's still looking a little bit on the fuzzy side, all those data points. If I do raw data over here, so the 2sum, this one, control, and I'm just going to make a quick scatter. It's still looking pretty noisy. So I'm going to have another go, and instead I'm going to set the number of scans to sum to 5. And I'm going to hit run again. And you notice that that was significantly faster than last time. And that's because this script is designed to pull the raw data from the Excel file rather than opening up the raw file again and finding all of that data. So this is starting to look a lot better. Let's say I'll do it for n equals, let's just do 10. This is going to be, we're going to lose a lot of resolution here, but that's okay. This is just an example. So you can see we're starting to lose a lot of all of this spiky stuff. And if I go into my Excel file, you'll find that I've got a new tab for 5sum, 5 normalized, 10sum, and 10 normalized. A few final notes. The first is that if you do use this script, please cite this paper that I've included in the script here. That's because these folks are the ones who wrote the ProDo Wizard program, and they should be credited for their work. A few other things that I would like to mention are that if you decide to add more species to this parameters list, so say I wanted to track an intermediate species and I discovered it after the fact, you can type that in, but you need to delete the raw data sheet. And that's because the program automatically goes through, if it finds raw data, then it will use that. So it will not find a new parameter and then go in and reprocess that at this time. Perhaps I'll write some functionality for that later, but currently as it is, you need to delete the raw data if you want to add more peaks. Also be aware that whenever the Python script saves to an Excel file, it gets rid of any charts that you may have added to that Excel file. This is because it's only designed to deal with data, not visuals. So if you want to add more sums after the fact, then take that into account. One final thing is that whenever you run this script on a new raw file, it will generate an MZML file, which is what the Python script is actually parsing. And so once you're all done with processing, you can delete this file. In many cases, particularly for long and data-rich experiments, you'll find that those MZML files can get very, very large. So keeping those in check is a good idea. It doesn't really matter if you delete it, because the MZML file can just be regenerated by the Python script. I think that is just about everything that I wanted to talk about, so thank you for watching, and I hope this makes your data processing life much easier.